All right. So in this lesson, we're going to describe the basics of spread spectrum, and we'll define what spread spectrum is and how it allows wireless to actually work and function. And it's a very important concept because without spread spectrum technology, we would not be able to use Wi-Fi. The clients would be locked into a specific frequency. If there was any interference on that frequency, then we would simply have to deal with that interference instead of allowing us to kind of hop through different frequencies. So the goals of this particular lesson is to really give you the tools that you need to understand how information can be sent using a Wi-Fi signal and the physics of that and the nature of that. We'll also take a look at the technologies that the inventors, the folks that invented Wi-Fi allow or incorporated into Wi-Fi to help protect and prevent from problems from interference. So we'll describe spread spectrum transmission technologies to help mitigate the impact of interference in a wireless network. We'll describe the different frequency spectrums that are available for wireless communication. We'll identify channel widths, right? When you're looking at the overall frequency range in the 2.4 gigahertz spectrum or the 5 gigahertz spectrum, they're defined and separated into specific frequency ranges for wireless communication. We'll talk about channels width and how they overlap if you have multiple APs deployed in the wireless network. And then we'll take a quick look at the configuration of the Meraki MR34 access point from the Cisco Meraki dashboard. We actually have some Meraki access points configured in our environment. Even though there's not officially a lab on Meraki, I will show you guys how to access that later so that you guys can play around with that a little bit later on. This is something that was just recently introduced into the process. I know that Cisco is also still offering, I'm not sure exactly where to find it, but Cisco is still offering the capability of actually getting your own Meraki access point by participating in some training online. I'm sure if you Google for that, you'd be able to find out where that is specifically, but I know Cisco is still giving away Meraki access points if you go through some training. So it might be something you guys want to look into. All right. The idea of spread spectrum transmission is very, very important to wireless implementation. When you send a signal, an electric field, which is what we talked about yesterday, that's being emitted at a specific frequency with a certain wavelength, that's how we generate the data, whether it's vertically polarized or horizontally polarized. That's how we generate the data that's transmitted and represents the ones and zeros that get interpreted as actual data. The only thing that you cannot control is the interference level of the medium over which that signal is being transmitted. And many devices might be using that same frequency range or even that same band of frequencies. You might even have some wider band applications that might be using multiple, a range of frequencies that would include the frequency that you're using specifically in your environment. So one of the main problems with Wi-Fi is how do we eliminate the interference that other devices cause, or how do we mitigate the impact of the interference on the signal that we're sending over that specific frequency. Wi-Fi clients transmit over an individual frequency. Even though we will see there is a band of frequencies that we can use, ultimately we're transmitting and receiving over an individual frequency. So in order to meet the need of mitigating the impact of interference on the signal, interference that other devices might cause, we use a specific transmission technology called spread spectrum. If a signal at a defined frequency, let's say for example 2.412 gigahertz, if I'm sending out a signal at that frequency and a nearby device emits a signal at the same frequency, then the first signal is going to get interfered with. It's going to collide with that second signal. Now, the impact of that collision does relate directly to the signal-to-noise ratio, right? Because that would be considered noise, even though it's within the same frequency spectrum. It's not really our original signal, so amplitude would come into play here. But in any event, there would be a collision. We would have radio frequencies that collide with each other. So the message that the first signal carries essentially gets jammed. And it's definitely true if the second signal's not intended to carry data, but it's just basically a result of a magnetic field that's caused by the activity of an electric engine or any kind of interferer in this particular case. If the first signal can emit in a range of frequencies or in a band, then you have some methods of kind of eliminating that issue, right? You can prevent the signal from being jammed because we can simply jump to a different frequency, one after the other. That's what we call frequency hopping. Or the signal can be sent over a larger frequency than the needed peak value of 2.412 gigahertz. So instead of sending at a specific tiny little frequency of 2.412 gigahertz, we decide to transmit over a range of frequencies within that range. The first technique, which is called the frequency hopping spread spectrum technique, the interference source might still affect the signal if it's wide enough or if it's powerful enough, and it's very difficult to predict what frequencies that interference will occur for that particular signal. But because the signal stays at the frequency for a short time, and in the case of most frequency hopping mechanism, that time is typically about 300 to 400 milliseconds, and then it jumps to another frequency, that interference doesn't really affect our transmission for a large amount of data. And because we're typically using TCP-based applications, and we have protection mechanisms in our communication control, we can mitigate the damages of the actual data that's being transmitted. The term spread spectrum comes from the fact that our transmission is spread over a large spectrum of frequencies rather than just an individual frequency. Now, there's been a progression of different types of spread spectrum technologies. FHSS being kind of that initial one, that frequency hopping spread spectrum technique. We also have DSSS, which is called direct sequence spread spectrum. This was the spread spectrum technology that was used by 802.11b Wi-Fi. And then we moved on to orthogonal frequency division multiplexing. We'll talk about that one a little bit later on. But in that second technique that I mentioned, interference is overcome by sending a signal around the interference. So instead of sending one signal at a peak frequency like 2.412 gigahertz, like I mentioned before, the signal gets spread over a large frequency band. The same information gets sent, but on all frequencies that fall within a particular range. So 2.401 to say 2.423 gigahertz. So that means we have a 22 megahertz or gigahertz wide channel. So if the interference that affects the emissions at 2.412 gigahertz happens, the message that gets sent around the distributed frequency is probably going to be heard because we're getting it from other frequency ranges. Okay? Now, it's called DSSS, or direct sequence spread spectrum, because the signal is spread over one large frequency in a directly larger signal instead of hopping from one frequency to the other. Now, obviously, from a theoretical standpoint, it's kind of important to understand this technology and kind of understand what it is about these terms and how these technologies are used. But in reality, you can't change the frequency hopping method for wireless. So from an implementation standpoint and from from a practical standpoint, having an understanding of these spread spectrum technologies is not really critical. but it is kind of useful to understand where we came from and where we're going to. An example of the use of DSSS is the way that radio stations transmit their signals. When you tune into a radio station, each station can be heard over a range of frequencies. We have digital dials now, so you can't really, I guess some of them you can still tune to micro frequencies, but if you had an analog dial, you could actually kind of move that dial across the board, and you would hear a faint transmission from the radio station, and as you tune into the main frequency, the signal will get cleaner and cleaner until you finally hit that sweet spot where you get the clear signal, right? So radio stations send their signals over a range so that they can be avoid being disrupted by narrowband interference. All right. Obviously, radio stations only announce their peak frequency, but actually, you could technically kind of tune in on what we call sideband frequencies from that peak frequency. In both frequency hopping spread spectrum and direct sequence spread spectrum, more than the peak frequency gets used. So the signal gets spread over a larger part of the spectrum. And again, that's why we call this spread spectrum technology. Makes sense. So I guess the question then is, which one is the best, right? Do I use FHSS? Do I use DSSS? Or do I look at something like OFDM, orthogonal frequency division multiplexing? Well, I think if you look at the technologies that are applied to the wireless standards today, OFDM has pretty much become the standard. And as we moved from FHSS into DSS, we actually increased the amount of bandwidth and throughput that we had with a particular wireless channel, even though we didn't change the overall nature of that signal, right? The frequency, the modulation, the polarization, it's all the same. Both of these technologies avoid interference that is centered on one precise frequency, a type of interference called narrowband interference. And that's really our goal, is to get rid of that narrowband interference. If the timers of the sending and the receiving stations are properly set, the devices that use FHSS, for example, hop to the same frequency at the same time, and they stay tuned. Okay, now keep in mind that would have to occur on both sides of the channel. But because it hops, the signal from the device that uses FHSS might lose only a few packets every now and then, whereas the signal from the device that uses DSSS might be more durable and less affected if the interference is in the middle of the emission zone. So there are some benefits to both. FHSS, for example, is more likely to cross an interference zone than DSSS. And that might be away from the interference, doesn't move from the frequencies around which it's being spread across. So if you're looking at it from kind of a pure interference point of view, it's very difficult to determine which technology is more efficient because it actually depends on the actual circumstances. DSSS definitely achieves a higher speed because it has a larger bandwidth to send data. And that's where you see when we used 802.11, the original version of wireless, we had a 1 megabit per second standard. But when we moved to 802.11b, which used DSSS, that went to a 10 megabit standard. All right, so even if you just take that aspect into account, that is the most important concept, right? Now I can get into some more of the specifics of the technique. I don't really need to speak too much to frequency hopping spread spectrum because it's not really used today. But let me get into a little bit more detail about DSSS, and then we'll kind of break down this spread spectrum technology, and then we'll get into OFDM. Like I said, DSSS stands for Direct Sequence Spread Spectrum. It's a spread spectrum modulation technique, and again, like I mentioned on the previous slide, the goal here is to reduce overall signal interference. So the spreading of the signal makes that wideband channel more noisy, but it also makes it provides for greater resistance to unintentional or intentional interference. A method of actually achieving the spreading of that signal is provided by the modulation scheme itself. And with DSSS, the message signal is used to modulate a bit sequence known as something called pseudo noise, or PN code. The PN code consists of a radio pulse that is much shorter in duration. In other words, much larger bandwidth than the original message signal. Now, we don't, like I said, we don't really need to get into the specifics, the technical specifics of the protocol itself. We're gonna do a deep dive in this particular lesson. It's not covered very heavily on the exam, other than just a basic understanding of the techniques. But it really gets to, it goes into the physics, right? The physics of this this spread spectrum technology. The 802.11b specification was the first one that introduced DSSS. There are several different components of DSSS. Let's talk about one of those components now, which is what we call Barker encoding. Okay. So whenever you're talking about any kind of transmission method, whether it's over an Ethernet cable or whether it's over wireless transmissions or whether it's over fiber optic cable, everything has to do with encoding. I mean, ultimately, what is the goal of any type of transmission, especially in digital communications? Well, the goal is to represent the ones and zeros, right? We're trying to represent data in the form of ones and zeros. So encoding is just simply a method that allows us to identify what those, or how those ones and zeros are represented, okay? And there are a couple of different encoding techniques that these different spread spectrum technologies represent. But we don't just simply send the actual bits that are being generated by the data stream, because if we lose any of those bits, the data stream becomes corrupt. All right. Now, in this course, we're not really supposed to go into a deep dive into signal theory. Like I said, from a practical standpoint, it's not really that necessary. You're not going to be changing how this encoding takes place. It's kind of like saying, well, how does Manchester encoding work in Ethernet? Well, do you really care? Ultimately, not really, right? But we will mention it just in passing here. So DSSS is used to send a signal over a spectrum, excuse me, that is wider than 1, that is needed just for the signal density use. Let me explain what I mean by that. Let's try and kind of keep it simple here. Consider that the net bit rate, how many bits per second we're trying to transmit, right? That's our net bit rate. It's usually close to about 1/2 the raw bit rate. In other words, what I mean is that without considering any kind of specific technique, a 2 megahertz wide signal allows about 1 megahertz of useful data to be sent. So there's an overhead, and then there's loss and other things that will occur. So we're going to get about half of the overall, or half of the signal is going to be useful for data. When we're using a spread spectrum technology, a 1 megahertz signal is sent over a bandwidth that's much larger than 2 megahertz. But what do we actually send to represent the data? The technique that is actually used in a Wi-Fi network consists of encoding the real information to send. So if I have to send a 1, for example, it gets encoded, meaning that it gets converted or transformed to a specific sequence of numbers. That's the whole concept of encoding. All right, and it is that sequence of numbers that is sent in parallel to represent the 1. Okay? The process of converting any signal into a data 1 or a data 0 is called encoding. Now, it might seem like, gosh, that's a lot of data. If you look at the encoding that's being depicted on the slide here, a 1001, we're sending, you know, in this particular case, 10 or 11 bits at a time. Why would I do something like that? Well, it's much easier, it's much more likely that I'm going to lose a 1 than I'm going to lose 11 bits of data. And I can extrapolate based on that 11 bits of information. I can extrapolate what that bit is supposed to be if I miss bits or bits are interfered with. All right. This is called the Barker Code 11 encoding method. And that's the first encoding scheme that we learn in this particular lesson. It was actually named from the name of its inventor, but there are many, many other forms. There's Barker Code 2 and Barker Code 5 and 13 and so on. And obviously you can derive from that there's 2 bits and there's 5 bits and 13 bits that represent the data. In this case, the Barker code is an 11-bit sequence of numbers. All right. Now, the whole purpose of this is to minimize the possibility that there's a misunderstanding of the signal in parallel signals being sent. Because like I said, you might not receive the entire signal, but you want to be able to identify what it is that you're actually seeing. Each digit of information that gets sent is run with something called an exclusive OR operation against this Barker code 11. Now, XOR operations, let me pull that up real quick. Boolean XOR operation means that if one or the other of the 2 bits that are being XORed is a 1 or a 0, then the output is a 1. And if one or the other are the same, in other words, both digits are a 0 or both digits are a 1, then the output is a 0. So I could say 0 XOR 0 is going to equal to 0 because both bits are 0. 0 XOR 1 is going to be equal to a 1 because one or the other is a 1. And 1 XOR 0 is equal to a 1, and 1 XOR 1 is equal to a 0. So that's our Boolean mathematical operation, XOR operation. And I think you've seen that when you're dealing with binary calculations in many, many different arenas, right? So when a 1 is to be sent, transforming it with the Barker encoding scheme will result in a sequence of 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 1. All right. Now, this is called the chips, or these are called, these long sequences of 1s and 0s representing that 1 digit is called a chip. If we're using the Barker code 11 with DSSS, that means that whenever there's a 1, then we send a different chip sequence, and you can see it here on the screen in parallel, and 0 conversely. So when you examine the numbers, you can see that as many as 9 digits of the chip can be lost, and the receiver can still understand that there's a difference between a 1 and a 0, right? They're kind of just inverse of each other, aren't they? So I could actually technically lose up to 9 bits of that chip sequence and still be able to identify which one's a 1 and which one's a 0. So on its face, obviously there's a lot more involved, and it's a lot more technical than what I'm describing here, but on its face, it basically looks very, very simple. Instead of sending the raw data, 1001, which of course would take less bandwidth, but the likelihood of corrupted information is significantly higher, we send these chipping sequences, and that's so that we don't lose the information, and we can better represent the information. We have techniques in other transmission options that allow us to identify whether or not data is corrupted and whatnot. And certainly we can do that at the data link layer using things like frame check sequences and CRCs and whatnot. But this is all done at the physical layer. Remember, we're talking about bits and bytes, encoding information. Now, another concept that's very important to understand is the concept of modulation. In DSSS, we have a couple of different modulation techniques, dBPSK and dQPSK. Modulation is essentially how do we change the signal to represent these ones and zeros. We do phase shifts to represent ones and zeros. And you can see it depicted on the diagram here. So we're actually shifting, we're not shifting the polarity, we're not changing the cycles, we're not changing the frequency, we're not changing the wavelength, which is your cycle. We're simply shifting the phase of the sine wave. And by shifting that phase, we're representing those ones and zeros. So modulation is not encoding. Remember, encoding is actually representing the raw data as chip sequences of ones and zeros, and modulation is a way for us to kind of represent how we see those ones and zeros. It's pretty straightforward when you look at the modulation technique, right? Remember, the Barker code allows us to send a chip of 11 digits, or symbols, right? Bits, I guess you could say, instead of the value itself, so that the signal can go through interference and still be understood. It makes very much, a lot of sense. But because the signal is spread over 22 megahertz and it contains 11 symbols that represent only one digit, like I said, if you go back and look at those sequences, I can lose up to 9 bits or 9 digits while going through interference of as much as 18 megahertz and still read that intended signal. All right, because again, we're not using narrowband transmission, we're using a wideband transmission over a 22 megahertz wide channel. So all these 11 digits are sent in parallel. The code doesn't specify how each part of the chip will be represented in the wave itself, the sine wave, or how will the wave be altered for the sender to identify and the receiver to identify what is a 1 and what is a 0. And again, that process is called modulation. This is a very interesting subject. It's not, again, necessary really for you to understand Cisco wireless and implementing Cisco wireless. From a theory standpoint, it's a really interesting concept. So I hope that even though maybe some of the specific technical aspects may be lost, you do understand the difference between chipping and modulation, right? A modulation is simply a way in which each symbol in that chipping sequence is represented within the sine wave itself. All right? So the first technique that was used to modulate a wave is called dBPSK. I guess we could spend hours and hours talking about these techniques and really get into the specifics of all of these different techniques, but it's not really necessary. Like I said, I'll go into some of the specifics, but PSK is just a phase shift keying sequence, right? And DBPSK is one of those phase shift keying sequences that's available. There are actually several different types. You can have amplitude shift keying or frequency shift keying or phase shift keying, and we're talking about phase shift keying in this particular case. You can do binary phase shift keying and what we call quadrature phase shift keying. We'll talk about that a little bit later on, the QPSK. It's actually part of this specification here, and it's also used in OFDM, where we have quadratures that we, or what we call quadriphase PSK, where you might have 4 quadrants, or you might have 16 quadrants, or 64 quadrants. And we'll get into some of the specifics. Now, you can really get into quite a bit of detail, obviously, with these modulation techniques, and spend a lot of time talking about these different modulation techniques. But we're not gonna do that. Let's talk about the dual polarization, dual band, phase shift keying first, and then we'll talk about the quadrature phase shift keying in a little bit. Okay, and get into some of the specifics there. So the first technique that we're going to talk about is this DBPSK. Complex name, but the operation is really simple, and you can kind of see it listed there on the left. It's the first diagram that you see on this particular slide here. A wave is a signal, a sine wave, that just simply goes up and down at a regular pace. We call that our frequency, based on wavelength and frequency. Frequency will represent how often that occurs within 1 second period, and the wavelength identifies the cycle, right, from peak to peak. But it's a sine wave nonetheless. It's polarized vertically typically. And keying means representing the zeros and ones. So we have to, a key is a way that we identify something, right? And that's what the PSK stands for, the phase shift keying. So a wave signal that goes up and down needs to be shifted, and the shift phase means to change the orientation of the wave. If the wave is going up, make it go down. All right? This modulation is done in binary, which means that we simply up or down, no other possibility can occur, right? Binary meaning there's only 2 possible options depending on what's being sent. So the DBPSK rule is very, very basic. When the next value to send is 0, do nothing. Continue sending the wave without any alteration. When the next value to send is a 1, shift the wave 180 degrees. That's it. So we see the first 2 ones, we shifted 180 degrees. The third bit was a 0, so we did no shift. The fourth bit was a 1, so we shifted 180 degrees. That should fall on that line, by the way. And then the last 2 bits are 0, so we did nothing. Very, very simple modulation technique. Very simple, easy to understand. Okay? In the best case scenario, if you're just sending all zeros, the signal's just sent unaltered. But what if you only ones need to be sent? Well, it's quite simple. Within each cycle, we shift every time. It's a very simple technique. It works very well because the rhythm of the transmission is known. 1 digit is sent each microsecond. So we're not talking about within a 1 second period. We're talking about microsecond periods. So 11 digits get sent in parallel. The receiver only needs to listen to the shape of the wave for the next microsecond to know whether the next value is a 0 or 1. If the next microsecond is unreadable because of interference or whatever it might be, 10 other signals are still going to be available in parallel to confirm or deny, I guess, the nature of that particular bit or that particular symbol. All right. So if you do the math, we're sending one symbol a bit, I guess, for lack of a better term. Each microsecond, that means we're sending 1 million symbols per second, which then converts to 1 megabit per second. Don't confuse modulation with the chipping code. Remember, we send 11 symbols in parallel, and each of those streams gets sent at a rate of 1 per microsecond, or 1 megabit per second. And because 11 symbols are being used to represent the one binary digit that we're trying to represent, if we have a 22 megahertz large signal, that's going to contain 11 parallel symbols, resulting in 1 meg of actual real throughput data. Modern networks today, they can't really operate at that speed. Remember, the 1 megabit standard was the original 802.11 standard that was defined when this Wi-Fi consortium was developed, and we started doing wireless in the beginning. So it's not it's not very practical and really not very usable in the case of modern networks today. So in order to increase the throughput, we simply change over to different signaling techniques. We don't change the frequency band. We don't change the 22 megahertz wide characteristics. We keep that intact, but we change how we manage that frequency spectrum. All right. So to increase the speed of DSSS, we use the same Barker Code 11 chipping process, but we use a different modulation technique called DQ PSK. Now, DB-PSK, that's just simply our binary, and that means that we only have two options, no shift or shift, right? So that's where the binary aspect comes in, DB-PSK, whereas Q stands for quadrature. There's only one letter difference between the two, but it really changes quite a bit how much throughput is available. You can see that DQ-PSK allows for 2 megabits per second of throughput, whereas DB-PSK only allows for 1 megabit of throughput. A little bit more complex, obviously, but does allow more data to be sent. And there's actually a couple of different steps that are used for this process. We start by grouping individual bits of the symbol into groups of 2. All right, so let me break it down. If the chip flow that's being sent is 1100, 101, 0010, shoot, let me go back. Let's just point at it here, right? If the chipping sequence is being sent as this or this, what we're going to do is we're going to break up that chipping sequence into groups. Now, in the case of DQ-PSK, the groups are broken up into 2-bit groups, right? Now, keep in mind, the data that's being sent doesn't necessarily represent, well, I guess indirectly it's going to represent the chipping sequence. So if I'm sending 1100, 1010, 01010, for example, I'm going to break up that flow of bits. That's not the chipping sequence, that's the actual bits that I'm trying to transmit. I'm going to break that up into groups of 2 bits together. So the 11 goes together, the 00 goes together, the 10 goes together, and so on. And you can see here on the slide, they've got the 00 represented at the top, the 01 is the second, the 11 is the third, and the 10 is the fourth, which are all the possible combinations that you're going to see for a 2-bit sequence. Okay, so we're able to represent twice as much data with a single waveform, if that makes sense, rather than doing just binary, where we're shifting the phase 180 degrees to represent a single bit. We can look at over a longer period of time the signal to represent 2 bits, and that's how we get that additional throughput. Okay. Now the symbols that are being used to send 1 bit after the other are still represented by these chipping sequences. And we're still sending the signals in parallel, just like we did before. So we're utilizing the frequency spectrum the same way, just we're able to identify things a little bit differently. Okay? So what's going to happen is DQPSK is going to determine one alteration of the wave to represent a group of 2 symbols. With a single alteration of that wave, you can represent 2 symbols instead of 1, which doubles the speed of the overall transmission. And by the way, this is a 4-QAM option, right? When you get into OFDM and you start to get into a 54 meg standard and faster standards, they simply start representing more and more quadrants, which now allows us to represent more and more data, right? More and more different sequences of bits. There's 4 possible combinations in this particular case, 0, 0, 0, 1, 1, 0, and 1, 1. So there needs to be 4 possible alterations of the wave. If the group to transmit is 0, 0, do nothing. Send the wave as it is. If the group to transmit is 0, 1, shift it 90 degrees. If the wave is going up, the signal should carry on from the top of the wave. If the wave is going down, the signal should carry from the bottom of the wave. All right. In this particular case, the signal was going up. We're talking about this one right here. The signal is going up, so we're going to carry on from the top of the wave. But it could easily be that the signal is also going down, and we carry from the bottom of the wave. But that would still represent a 90-degree phase shift, which would still represent a 0, 1. So the angle, whether it's positive or negative, doesn't really matter in this particular case, because it's a shift of 90 degrees. That's what defines the 0, 1. Okay. If the group to transmit is 1, 0, we see that at the bottom. We're going to turn 270 degrees or minus 90 degrees. So the opposite of the 0, 1 sequence. If the signal is going up suddenly, we should carry on from the bottom. If the signal wave is going down, carry from the top. Same concept, still represents the same bit pattern or bit sequence. If we're trying to transmit a 1, 1, we turn it 180 degrees. And you can see that here. I don't really need to get into the details. So it's a really interesting way of using the same frequencies, right? The same, well, I guess I should say, because this is all happening in that microsecond window to represent twice as much data because we're simply looking at these different phase shifts. All right. Even though today a 2 meg standard is still not going to be significant enough for us to be able to get the throughput that we need to be able to transmit and receive. So obviously we go ahead and we look at other modulation techniques. And another one of those modulation techniques is CCK. All right. Oops, sorry about that. And we'll take a look at this. Now you can see that we're not only looking at shifting the signal on a, in a phase approach, we're actually looking at the polarization as well. So, obviously a speed of 2 megabits per second might have been sufficient for some very basic applications at one point, but it's really not fast enough for modern networks today. And quite frankly, even dealing with this modulation, any kind of DSSS modulation today is really not going to be sufficient. But we always have to know where we came from to be able to know where we got to. So we can't really make the signal go any faster by keeping the Barker 11 encoding scheme. We can't shift more than 90 degrees, obviously. So if we did, like if you went to an 8 shifting technique instead of a 4 shifting technique, you might miss one of those shifts within that short time period. and the data might not be represented. All right. So to increase the speed in modern, for lack of a better term, in modern DSSS modulation techniques, we use CCK. CCK uses a group of 4 bits, and it encodes them in chips of 6 bits each instead of 11 bits, right? So we had an 11-bit chip to represent 1 bit of data, but in CCK we group data into 4 bits, and we encode each of those 4 bits using a 6-bit sequence, if that makes sense. We then associate a complex and unique symbol for each chip. Each symbol is a combination of phase changes that use the DQ-PSK that we talked about before. So we have 4 angle rotations of 90 degrees. Each symbol is unique, and it's represented by a sequence of phase shifts. You can kind of see it listed here, right? If you look at this on a spiral, or look at this, this is the flow of data, and these are the phase shifts that we're referring to, and we can see that there are multiple phase shifts to represent a sequence or a bit pattern. All right. Now it does appear that there are more than 6 here. I don't know if that was intended or not, but we know that we use 6 chipping sequences in 6-bit with 6 bits each for each to represent each of the bits in our group of 4 bits. All right, but the point here, and it's really the most important aspect, is each symbol is a unique sequence of phase shifts within the wave itself. All right. Now CCK does use DQ-PSK to represent those symbols, but because there are 6 bits in each symbol, there are 64, which is 2 to the power of 6 different symbols that we can represent, because we're using binary math. So 6 places, 2 to the power of 6 is 64. Each one of those represents a unique 6-bit chip. So to each 6-bit chip, 2 bits get added. That's going to result in an 8-bit long code symbol. And so the 2 bits at the beginning are added to represent the orientation of the beginning of the symbol. So that's where they get the additional bits in this particular diagram here. The remaining 6 bits represent the chipping sequence itself. All right. Maybe a little bit more confusing. Certainly I understand that. But what this did is this allowed us to increase the bandwidth significantly over the process of still using the same, essentially the same modulation techniques, right? We're using the same frequencies, the same wavelengths, and so on, but we're not, and we're using the same bandwidth, right? The same 22 megahertz wide channel. So we send the wave over that 22 megahertz wide channel. It's a little bit faster than we saw with the previous encoding methods. We send it at a speed of about 1.3 million code symbols per second, each of those representing 4 bits. So if you do the math, you multiply those numbers, 1.3, I forget what the actual full number is. I think it's 1.37 something, but we multiply that times 4. That's going to give us our 5.5 megabits of throughput. That's what they're listing there in the book here. All right. Obviously much faster than Barker 11 with DQ-PSK. In later versions of CCK, we use the 2 bits that come before the 6-bit chip, not only to give us the orientation of the symbol, but to allow that same symbol to represent 2 different values, depending on the initial 2-bit orientation of that symbol. So this allows us to have 8 bits instead of 4 bits in each 6-bit chip, meaning that we doubled the speed. So we went from 5.5 megabits per second to 11 megabits per second. And that's essentially where we get to 802.11b. The higher the speed, obviously the more sensitive the wave becomes to interference, multipath distortion, etc. But we do get a much faster throughput. If CCK is used at 11 megabits per second, altering the first 2 bits is enough to render the chip kind of unreadable. So frame check sequences might not match what we expect at the data link layer. We don't really need to go beyond that. I think, you know, hopefully this kind of makes sense. I'm pretty sure that you guys are okay with what we talked about in this scenario, right? I think it makes sense that we, you know, how we're representing these bits in the Barker 11 process. But maybe the CCK one is not as easy to understand. It's, by the way, it's called complementary code keying. Okay. I guess I can kind of try to describe the CCK process a little bit more. It's a modulation technique, like we said. Was introduced in 802.11b. That was the first time that we saw this modulation technique introduced. I think it was in 1998 or 1999 that occurred. It, you know, obviously was introduced to achieve a much higher data rate than 2 megabits per second. So let me kind of just hit some high points one more time and then we'll move on. Much shorter chipping sequence, right? Barker 11 was what we used in the 1 meg and the 2 meg standard. 8 bits in this particular case, as you can see from the diagram. Each one of those kind of squares that are phase shifted 90 degrees or 180 degrees or whatever, these represent those 8 bits in our chip sequence. So that means that less spreading to obtain a higher data rate, but much more susceptible to narrowband interference, you know, which then results in a much shorter transmission range, by the way. So there was a trade-off. There is a much shorter transmission range. But beside a shorter chipping sequence, we also have more chipping sequences to encode, more bits. So 4 chipping sequences, like I said, at 5.5 megabits per second, 8 chipping sequences at 11 megabits per second. That's going to increase the data rate, like I said, up to 11 megabits per second. All right. Barker code only has one single chipping sequence. One that represents a 1, one that represents a 0. Which is why it's called binary. All right. Yeah, I don't think we need to get into any more detail on that. I think we're good there. Now we get into what we call orthogonal frequency division multiplexing. Now, OFDM, which is really the modern modulation technique that we see today in wireless networks. It stands for orthogonal frequency division multiplexing. Is a method of encoding digital data over multiple carrier frequencies. It's the modulation technique of preference in wideband digital communications like digital television, audio broadcasting, wireless networks, of course. 4G mobile communication uses OFDM, lots of other applications for OFDM. When we're dealing with coded orthogonal frequency division multiplexing, we have forward error correction and time frequency interleaving that get applied to the signal that's being transmitted. This is done to overcome errors in mobile communication channels primarily affected by multipath propagation. OFDM was actually developed in the mid-'80s, I believe it was. It came out as a modulation technique. but it wasn't really adopted to wireless until much, much later. The main advantage that you're going to see with OFDM over a single carrier scheme is the ability to cope with severe channel conditions, high attenuation, narrowband interference, frequency fading due to multipath distortion, etc., without having to have any kind of special technique. We can talk about how we introduce additional speed from this perspective as well. Obviously, as networks got faster and faster, you know, we started with a 1 meg standard, then we went to a 2 meg standard, then we went to an 11 meg standard. Well, you know, when we're going into twisted pair Ethernet and 10-100 networks, 100 megabits per second is much, much faster than 11 megabits per second, especially when you consider the concept that 11 megabits per second is in a contention-based scheme as opposed to a non-contention-based scheme. So again, we have to come up with another modulation technique to adapt to these higher speeds. So this modulation technique that was found was OFDM. Like I said, OFDM was already being used in radio transmissions, and it offered almost a perfect play to replace DSSS for our Wi-Fi networks. But the frequency spectrum is divided up significantly differently than when we dealt with DSSS or even FHSS. Instead of using one large 22 megahertz wide channel, OFDM actually divides the carrier into 64 subcarriers, and that's kind of what you see depicted here on the diagram. These subcarriers are called tones. They're about 3.1 or 3.2 kilohertz apart. So 48 of the subcarriers are used to carry data, and then the other 4 are used to control the communication. And so the concept, right, is to allow us to have multiple kind of narrowband frequencies that we can use to transmit our data. All right. There are 12 other carriers added, right? I said we have 64 carriers, and then we add 4 others for controlling communication. But with those 52 carriers, we get 12 others that are added, which are sideband channels, used as guards, right, to distinguish one main carrier from the next, so we don't have overlap between these subcarriers. So it is 64 subcarriers, and that's the 52 plus 12. So if you do the counting here, you can kind of see what each one of those represent. And we can see that that we have the sideband channels, and then we have the carriers in the middle. All right. To distinguish the main carrier from the next, and we also have kind of a narrowband frequency in the middle that's also marked, that allows us to mark the center band, right, the center of the carrier, because the idea is that as you move to the center frequencies, you're going to have higher fidelity and less interference and so on. All right. So just to reiterate, you have 64 subcarriers. Only 48 of these subcarriers are actually used to carry data. That would be represented by the blue ones here on the screen, and the red ones as well. Okay. The great advantage of this system is that if 48 channels carry the data, each channel can transmit slower than CCK channels, and the group of 48 will still achieve a higher throughput. Right? So for example, if each subcarrier is sending at 1 megabit per second, the total speed of 48 megs per second gets achieved because we're combining this information. So not only is OFDM faster because each channel transmits more slowly, meaning that it has to work less, right? It bears less density of the symbols per millisecond. it becomes more resistant to multipath distortion. Because there are so many channels, some can be affected by interference, but the others can still offer normal communication. Remember, the whole idea here is that we're transmitting data over all of these channels at the same time. And the idea is that if any of those channels are interfered with by a narrowband interferer, that information gets corrupted, but we still have other channels to work with, to interpret the data. All right? Keep in mind, OFDM is a standard that was introduced in 802.11g. That's our wireless standard 802.11g. So when we went from B to G, we went to OFDM. But G still operates in the 2.4 gigahertz spectrum. And we're still dealing with a 22 megahertz wide channel, right? Let me do a little math here. Times 64. Yeah. So in this particular case, 20 megahertz. But if you take the 312 or whatever, I may not have done my math exactly right, but remember these subcarriers are microchannels, I guess you could say. They call them tones, but they're only 312 kilohertz apart. So if you multiply that 312 kilohertz by 64, you do get that 20 megahertz wide channel. It's 22, but you know, there's a little bit extra. So this dotted line that you see represented here represents the original channel that we were using in DSSS, right? That 22 megahertz wide channel. And this is how that 22 megahertz wide channel is being divided up in OFDM. So we're not actually changing the physical frequency range that we're using in this case. Now, when you go to 802.11a, that changes completely, right? We're in a completely different spectrum at that point. We're in the 5 gigahertz spectrum, and there's a significant difference there. All right. Now, one of the main, or one of the important features of OFDM is the way that it manages tone overlapping. Remember, each one of these individual humps that you see here is called a tone. If you look at the drawing of the OFDM channels, you'll see that the subcarriers are close to one another. And I don't know if you can really tell on this diagram, but they actually kind of technically overlap, meaning there's no gaps between the tones. That means that the shoulders touch each other. This could cause interference between the frequencies, but OFDM considers not only the electric field, but also the magnetic field. Each channel is sent with an angle of 90 degrees compared to the two channels on either side. So this is a three-dimensional transmission rather than a two-dimensional transmission. Not only are we going to do phase shifting in the sine wave, we're going to change the polarity. So you have to kind of look at it like a corkscrew. Along a string or a line, you've got this corkscrew kind of effect. We'll take a look at the modulation techniques and identify how modulation occurs. It's actually just about the same. We use binary phase key modulation, and we use Quadrature phase key modulation. So same concept. A shifting pattern represents a specific pattern of bits. Obviously, OFDM relates to how the wave is sent. It's not a DSS technology, but it's very close. In other words, how it occupies the channels, like I said, that 20 megahertz channel. So if you looked at a 802.11g spectrum, or you looked at an 802.11b spectrum, you have the same 11 or 13 channels, depending on what country you're in, and they have the same 5 megahertz gap between the 22 megahertz wide channels and so on. So the channel occupation and the frequency occupation is the same. Each tone is considered to be an independent carrier that actually bears data. So the OFDM mechanism ensures that the carriers do not interfere with one another. All right. Now there is a specific coding technique. Each frame comprises part of the layer 1 preamble that's designed to prevent confusion between the tone that is being sent to any other tone that might be sent. But there's only one way of coding, and we have to use a specific preamble sequence of digits as an identifier to distinguish that. Now there are several ways to represent these digits within a tone. The simplest way is to use your binary phase key, phase shift key. Slightly different than the DSSS binary phase shift keying that we saw with the DSSS modulation. Remember, in that particular case, we were shifting 180 degrees to represent a single character, a single symbol. In this case, we're doing our phase shifting over time to represent 2 symbols, right? So it's quite simple. If you remember, let me go back to it real quick. With DBPSK, when the next value sent has to be 0, do nothing, continue sending without altering the wave. When the next value to be sent is 1, change it 180 degrees. So if we're sending a whole bunch of 1s, we continue to shift. In BPSK, which is what's applied to OFDM, when the next value to be sent is the same as the value that was just sent, do nothing. All right, we actually don't see that in this particular case. All right, so if I was sending a 1-1 followed by a 1-1, the sine wave would just continue. All right, unfortunately we don't see that depicted here. Actually, you kind of do see it depicted down here, right? Here's where I'm sending a 1 and a 1, so we're not shifting. Actually, now that I look at that, that's a representation of DBPSK as opposed to just BPSK. But let's take a look at some of the other options. When the next value to be sent is different from the value that was just sent, a 0 following a 1 or a 1 following a 0, we shift 180 degrees. Change the direction 180 degrees. Okay? So if we're sending a multiple of 1s, we should only shift 1 phase shift, as opposed to down here where we're not shifting at all, right? So let's see if they have it. Yeah, they have it right here. So 0, 1, and then 1, 0, they shifted 180 degrees one time. The difference between DBPSK and BPSK is the reason for the shift. Getting a 1 versus getting a different value. BPSK does not differentiate 1s and 0s, or any change causes, doesn't differentiate 1s or 0s specifically. It's just kind of like any change causes a shift in the pattern. All right. I don't know if that makes sense. I probably didn't describe that very well. Hopefully the diagram helps out a little bit. But with BPSK, each carrier is 125 kilobits a second of information, which implies that we have 48 tones, as we saw on the previous slide here. These blue arches, I guess, for lack of a better term, represent the tones, which results in 6 megs of throughput at a minimum. All right. Now you can increase the density of the information per subcarrier. It can go up to 9 megabits per second if you do maybe say 187 kilobits per second per subcarrier. We can do this because OFDM prefers to send redundant information. So just like we saw with DSSS, we want to make sure that the message is received even if some bits are lost. At 6 megabits per second, half of the bits are information and half are redundant. At 9 megabits per second, 3/4 of the information is the 3/4 of the bits are the actual data, and only 1/4 of the information is redundant. Obviously, the higher density is going to indicate that we're going to be more sensitive to interference and so on. To go higher than 9 megabits per second, which would be required if we wanted to use this encoding method to do better than CCK for DSS, we use something called Quadrature Phase Shift Keying, or QPSK. Very similar to the DSSS QPSK mechanism. Obviously the D is not there because D is for DSSS. But we still send data in groups of 2, a 0, 1, a 1, 0, excuse me, a 0, 0, a 0, 1, a 1, 0, and a 1, 1. If you remember, let me go back to it again so I can show you guys visually. If a group to transmit is 0, 0, we do nothing. If the group to transmit is 0, 1, we shift it 90 degrees. If the group to transmit is 1, 0, we shift it 270 degrees. All right. Now with QPSK, which is the Quadrature Phase Shift Keying that we use for OFDM, if the next group to send is 0, 0, we shift that 270 degrees. If the signal is going up, the signal should carry only from the bottom. If the wave signal is going down, it should carry from the top. In this particular case, it carried from the bottom because the signal was going up in the previous 2 bits, or the previous group. All right, if the group being sent is 0, 1, we shift that 180 degrees. You can see that shift here. Again, if the wave is going down, we shift up. If the wave is going up, we shift down. If the group that needs to be transmitted is 1, 0, we turn that 90 degrees. In this case, it's going down, so we shift up. If it was going up, we shift down. It would always, always depend on the previous group, right? Because it's the actual shift that identifies the grouping. It's not whether it's on the positive side or the negative side. And if the group to transmit is 1, 1, we do nothing. All right, we don't see that in sequence here because we started with a 1, 1 in this particular case. I know it's a lot of information, and I'm sure it's not particularly clear. Hopefully it's enough for you to be able to, if you decide to get into this spread spectrum theory and really dive into it, which a lot of people don't, you can always, with this foundation knowledge, go out and kind of identify more specifics and look at some specific RFCs or engineering documents and whatnot. But again, not required for this class. Obviously it is a fundamental component of wireless, right? It's a very important concept to understand within wireless from an engineering standpoint, from a design standpoint. QPSK is essentially like a reversed DQPSK. All right. But why would I use one instead of the other? Some people consider the differential method to be more robust than the non-differential method that we saw with DQPSK. Obviously, we can see from a bandwidth perspective, there's a significant difference. With QPSK, each carrier bears 250 kilobits a second. That allows us 12 megabits of total throughput. But we can increase that density, like I said, to 375 kilobits per second per tone, which gives us 18 megabits a second of throughput. Now, when you think of 802.11g, you say, well, wait a minute. 802.11g is a 54 meg standard. But yet they're talking about 12 megabits of throughput or 18 megabits of throughput. So that's not even close to the specification that we were talking about previously. So why? I mean, how do we get that additional bandwidth? Well, this is where QAM comes into play. All right, and I promise we're almost done with these different this theory. We still have quite a bit to cover with regard to the channels themselves, more practical application and taking a look at channel assignments and so on, but which is definitely something you definitely need to know from an engineering perspective and an implementation perspective. But we get into QAM, right? Now that we have kind of an understanding of the different techniques, QPSK and DQPSK, we know that they work in a 3D model. So not only are we doing shifting of the sine wave to represent sequences of bits, we're also doing 90-degree rotations. All right. And you kind of have to, when you're looking at this matrix here, you're looking at this diagram, it's like you're looking down a pencil, right? And you've divided the quadrants or the areas on the top left and right and the bottom left and right of that pencil into different quadrants based on rotation, if that makes sense. Hopefully that makes sense. Let me describe, before I get into kind of the specifics, this whole concept of quadrature amplitude modulation. It's used in digital situations. It can also actually be used in an analog situation as well. In the case of digital, we shift phases each by 90 degrees, which is why it's called quadrature, because we have 4 quadrants in that particular case. So that's why that's how we got the name of the scheme, the QAM. The modulated waves get summed up together, and then the final waveform is a combination of both the phased shift keying concepts that we learned in the previous slides and amplitude shift keying, which is what we're going to learn about now. All right. In analog, we use something called phase modulation, but we don't use that in digital transmissions. In the case of digital QAM, we have a finite number of at least 2 phases and at least 2 amplitudes that are used. Okay? PSK modulators are often used using this QAM principle, but they're not actually considered as QAM since the amplitude of the modulation carrier signal is constant in those particular scenarios. So it's a very similar concept, but now we're working with amplitude modulation as well. It's obviously used in 802.11 standards, but it's also used in a lot of other applications. So let me try and kind of describe what you're seeing here in this particular slide. With the rotations of 90 degrees, whether they occur actually by the electric field changing the orientation, or virtually by the field staying vertical but we're changing the shape of the field, it allows the wave to have 4 different directions. You can send the wave up, you can send the wave left, you can send the wave down, or you can send the wave right. Does that make sense? Think of it as like the horizontal plane and the elevation plane, although that's not really exactly true, but that's kind of the concept. If I hop from one direction to the other, that is essentially the principle behind QPSK and DQPSK. Obviously, because we're actually shifting the electric field or changing the orientation of the waveform, these techniques need to have new radios, you have to have new hardware, it's going to consume more power as well. To obtain QAM, sounds like some Zen state that you would be in. To obtain QAM, the only other parameter that's needed to change is the amplitude, the height of the wave, the height of the wave. We're not modifying the frequency or the wavelength. All the modulation techniques that you've seen up to this point changed the orientation of the wave but kept the wave at the same size. We never talked about amplifying the wave or applying attenuation to a wave. With QAM, we actually have 4 different amplitudes or 4 power levels. Null, which is no signal, low, average, or high. So that kind of identifies those 4 states that we talked about. OFDM actually specifies that each tone can have a different orientation. Each one of those narrowband subchannels can have a different orientation, up, left, down, or right. The signal strength information can then be coupled with the signal orientation. Just follow along. Hopefully, as I kind of progress through the discussion here, you'll get a better understanding of what I'm talking about. 4 amplitudes, like I said, null, low, average, and high, are multiplied by the 4 directions, which creates 16 different possibilities. All right? This is why it's called 16 QAM. Now you can guess that 64 QAM and 256 QAM is going to use different techniques to represent larger bit sequences. Now, remember, this is a modulation technique. And the whole purpose of any modulation technique is to be able to look at what's happening at the physical layer with a waveform. Whether it's the amplitude, whether it's the frequency, whether it's the phase, whether it's the polarity, whatever. Take a look at a waveform and be able to interpret the ones and zeros that are represented by that modulation. All right, with 16 QAM, that allows 4 bits to be coded by a single symbol. That's 500 kilobits per second per carrier, 24 megabits per second total, right? 500 kilobits per second per carrier, which gives us 24 megabits per second. Now, there's, like I said, 64 carriers, but we're not using many of them, right? We have, there's a few of them that are used for other purposes, as I mentioned before. Okay. Remember, we have the 4 bands for control, and then we have the 12 bands for the sideband channels and the center band and so on. In any event, 500 kilobits per second per carrier. If I multiply that times the number of carriers, you're going to get your 24 kilobits per second, or megabits per second. And there's only 48 carriers. But even though there's 64 of these subchannels within the 20 megahertz wide band, we only have 48 carriers of actual data. So with this speed, only 1/2 of the bits are redundant. To make that sure the signal is understood, obviously, we want to make sure that if there is interference, we can still understand the signal itself. By increasing the density of the useful information to 3/4, like we did before, like we talked about before, now we have 750 kilobits per tone times 48, which gives us 36 megabits per second of throughput. To increase the speed even more, OFDM actually can use a 64 state QAM. Behavior is pretty much the same. The only difference is that there are 64 possibilities, 64 symbols, and 8 bits are coded in each symbol. 2 to the power of 8 is 64, or 8 bits, excuse me. So 64 QAM allows 1 megabits per second per carrier, which then gives us a speed of 48 megabits per second. And 2/3 of the bits are information bits and 1/3 are redundant bits. So it's simply a matter of increasing the ratio. If I increase the ratio to 3/4 of the information and 1/4 is the redundant bits, then I get to that magic number that we're all used to seeing with OFDM, which is 1.125 megabits per second per carrier times 48, which gives us a speed of 54 megabits per second. Okay. High density modulation schemes like 64 QAM are used by 802.11n, and that's where we get the 8x8 quadrature concept. And we can even go higher. We can go up to 256 QAM. 802.11ac uses that, 256 QAM. That's going to give us a 16x16 quadrature. which is a much higher data rate, obviously, in the technique. Now, when you go up to 256 QAM, you're talking about using 20 megahertz wide channels or even possibly 40 megahertz wide channels. We'll get into those concepts in a little bit. All right. When you're dealing with data rates based on channel width, spatial streams, proximity, technology, we'll talk about all that in this chapter. We'll wrap up this chapter by discussing that, or those specifics, I should say. Okay? Bear with me. We've got a little bit more to do here in this particular chapter, but let's get into the stuff that is more practical, right? The stuff that you actually do need to know for the exam, and also you need to know just from a practicality standpoint from an implementation perspective. And that is, how are the frequency spectrums allocated to the different wireless standards, right? What frequency ranges are used? How is this ISM band reserved by ITU? The International Telecommunications Union is the one that kind of specifies this for that radio frequency industry for the industrial, scientific, and medical bands. Worldwide, the frequency ranges that are generally acknowledged in the 2.4 gigahertz range and the 5 gigahertz range are 2.4 to about 2.5 gigahertz and 5.725 to about 5.875 gigahertz. Okay. Now, different countries allocate these different bands differently. See if I can say different more times in a sentence, but and we'll take a look at those specifications. In the United States, of course, that is going to be regulated by the FCC. And the original FCC specification states that the UNII 1 band is what we use for indoor use only. UNII 2 band is intended for Wi-Fi bridging for both indoor and short-range outdoor applications, and the UNII 3 band, which provides for much higher transmission power levels and antenna gain, is preferred for long-range outdoor wireless bridging. You can kind of see the ranges here for UNII 1 and UNII 2 and UNII 3. And then we have an extension of UNII 2 with an additional 11 channels. You're not going to need to know specifically what these frequencies are on the test, but I do want to point out which ones are used for which specific purpose, right? The 5.15 to 5.25 gigahertz range, that's mainly indoor in the USA. For ETSI, which is the European equivalent to FCC, which is called Band A, is indoor use as well. 5.25 to 5.35, indoor/outdoor in the USA. For ETSI, it's more indoor as well, kind of defined as Band A as well. UNII 2B, we don't see that one listed here. We see the UNII 2 extended, but we don't see the 2B. That's the 5.35 up to 5.47 frequency range. It's still kind of being reviewed. It's not really ratified as a standard in both the FCC and the ETSI regulatory commissions. 5.47 to 5.725, that's our extended range, and the FCC identifies that as either an indoor or an outdoor frequency range. In ETSI, it's defined as business-to-business mobile communication. 5.725 to 5.825, which is the last one that you see here. We call these the ISM UNII 3 bands, mainly outdoor use. Okay, and in Europe, under the ETSI regulations, outdoor and licensed. All right. Another one that you don't see here, 5.850 to 5.925. That's your UNII 4 band. Still under review. but proposed for the future use. All right, so let's talk about that 2.4 gigahertz ISM band and how this radio frequency is divided up. The ITU designated the 2.4 gigahertz spectrum as unlicensed. It's part of that ISM frequency spectrum. Each channel is 22 megahertz wide, so you can kind of see that depiction here, 22 megahertz wide for each channel. So if you look at the overall spectrum, right, which in that 2.4 gigahertz range goes, well, I guess technically it goes from 2.4 to 2.4835 gigahertz up to 2.4970 in Japan, which allows for 11 channels in the United States and up to 13 channels in Europe and 14 channels in Japan. That's why you see a designation of 13 and 14, but in the United States it stops at 11. But because we have these 22 megahertz wide channels, right, and there are 5 megahertz gaps between them, notice they don't, the shoulders don't touch each other in this particular case, we only have 3 channels that won't overlap. Channel 1, Channel 6, and Channel 11. And I think this is something that you guys are probably already familiar with. I mean, it's a pretty common knowledge today that within this spectrum, there's 3 channels that don't overlap with each other. Because of the limited number of channels and the usage by other devices, particularly in this frequency range, we have Bluetooth, cordless phones, DECT phones, microwaves, etc. The 5 gigahertz band offers more bandwidth options, and we'll see that in a minute here. But this is how the frequency spectrum is broken down in the 2.4 gigahertz range. The center frequency for channel 1, 2.412. So if you subtract 11 megahertz off of that, that gets your beginning frequency, and add 11 megahertz on that, that gives you your top end frequency. And you can see the center frequency for each of these channels, all the way up to 2.462. 2.462, let's see here, 2.462 plus 11. Oops. Oh, yeah, we can't really do it that way. It's gigahertz. Never mind, but you get the idea. 22 megahertz wide. Center frequency obviously is the center frequency of that channel. All right. Now, remember we were talking about DSSS, because this is the same frequency spectrum that was used for 802.11b and 802.11g. So we were talking about the frequency hopping mechanism that we used within this frequency range. And we used 20 megahertz of this in OFDM to transmit data, 22 megahertz of this in DSSS to transmit data, because it was a wideband frequency hopping mechanism. But the overall specification didn't change at all, right? Whether it's 802.11g, 2.4 gigahertz, or whether it's 802.11b with DSSS, 2.4 gigahertz, the frequencies are used the same way. Does that make sense? Hopefully, going through all that pre-discussion that we went through kind of, starts to make things a little bit more clear when you start to look at how this frequency is allocated and utilized. Now, the 5 gigahertz band, obviously operating in a much higher frequency, has different limitations. Restrictions are varied between the 5 gigahertz bands for transmit power, antenna gain, antenna styles, usage, and so on. Each country is going to have their own restrictions for this particular band. Let me try and break down what you're seeing on this slide here, because it can be a little bit confusing. You can see the 5.15 gigahertz range to 5.25 gigahertz range, which is what they call the UNII-1 or lower band. FCC limits the power of this particular lower band or lower frequency range to 17 dBm, and it's identified as for indoor use only. Okay. ETSI says that you can have an effective isotropic radio power of about 23 dBm in this case. From 5.25 gigahertz to 5.35 gigahertz, which is the UNII-2 specification, the middle bands, transmit power of up to 24 dBm by the FCC, up to 23 dBm with ETSI. 5.47, now we're shifting down to the next diagram here, 5.47 up to 5.725 gigahertz. This is called the UNII-2 extended range. Transmit power here by the FCC, 25 dBm. The EIRP that's defined by ETSI is about 30 dBm in this case. And then the last is the UNII-3 ISM, 5.725 to 5.825, 30 dBm by the FCC and 30 dBm by ETSI. Again, not something you need to know for the exam, but you know, it's when you're dealing with purchasing radios and antennas and installing a system, you kind of should know the rules, right? You don't want to be transmitting at 40 dBm when you're only allowed to transmit at 23 dBm or 17 dBm on UNII-1. All right? In the US and ETSI domains, the same 8 channels. Okay, pay very close attention to this, very, very important. The same 8 channels, which are, let me see if I can, 36, 40, oh gosh, 44, 48, 52, 60. Oh, they're in the diagram there. 64. I'm trying to think of these from the top of my head, and I just realized they're on the diagram. The ones that are listed on the top diagram there. 36, 40, 44, 48, 52, 56, 60, and 64. These are allowed in both the UNII-1 and the UNII-2 spectrums. In the extended spectrum, we have 11 channels, 100, 104, 108, 112, 116, 120, 124, 128, 132, 136, and 140. Those are allowed in both the US and the ETSI domains as well. The US domain only allows 149, 153, 151, 157, and 161. That's the UNII-3 band. In the ETSI region, Europe, those channels are not usually available. So that would be very conducive to what you might see as a test question on the test. You know, which channels fall within which range, right? So we can see that from we have 30 megahertz between the center channels from on the low end shoulder and the high end shoulder, and then we have 20 megahertz between each channel. Very similar to what we saw with OFDM's use of the 2.4 gigahertz frequency range. Now there are some additional schemes that are available today where we're not dealing with 20 megahertz wide channels anymore. We're dealing with 40 megahertz wide channels, and there's all kinds of ways of utilizing and managing these channels to provide additional features. Well, we might get into that in this chapter. I'm not sure if we get into it too much. I know we do talk about, yeah, we'll get into channel aggregation a little bit later on. I'm pretty sure of it. Probably a few slides from now here. All right. The 802.11 AH specification. Supposed to be finalized by 2016. Now this book was published in 2015, so I'm not sure. I have to go back and see if it actually has been approved as a standard. But the frequency ranges will vary by country, but it's under the 1 megahertz spectrum. All right. Now, when you think about that, that's a very, very, very low frequency, sub 1 gigahertz, right? Due to that frequency, the range will be much, much greater than, say, 2.4 gigahertz or 5 gigahertz. What would this be used for? Most probably it's going to be used for sensor networks, like we talked about, like Zigbee devices. You know, when we're dealing at much, much lower frequencies, the power consumption is a lot less. So there's a lot of power saving that goes into it. There's a lot of throughput enhancements, but you can see the range is about 0.6 of a mile, which is pretty significant when you start to consider wireless. Now, the data rates, yeah, they're not that significant, right? 100 kilobits per second to 40 megabits per second. But if it's for sensors or controls or low bandwidth applications, it can be very, very useful. Probably not something that, that you guys had seen listed before. There's another one as well, 802.11af. Right, the AF specification was actually approved in 2014. It's called the TVWS, or Wi-Fi, or Super Wi-Fi. All kinds of interesting names for it. Less than 300 megabits per second, but a range of 3 miles. All right. Now you can see the spectrum, ultra high frequency, 470 to 698 megahertz. That's less than the 2.4 or 5 gigahertz range that we talked about, but this is in the UHF spectrum. Remember there was a movie called UHF, I think? It was an interesting movie. But most likely it's going to be used for like broadband, cellular offloading, you know, in rural areas. It's a registered frequency range. One issue with AF is the lack of certification right now. There's not a whole lot of common frequencies. But again, not something you're going to see in your enterprise, obviously. But it's nice to kind of know what some of these other standards are. There's actually many, many different modern standards today that are being developed for lots and lots of different applications. 2007, we came up with 802.11y, another sub 1 gigahertz spectrum standard. Much higher EIRP, up to 20 watts. Wow, that's pretty significant. But you know, this is used in this is a registered licensed band, high gain antennas, long distances, usually used for linking buildings or facilities or whatever. You have to pay a fee. And then you have to pay fees, I believe, for the stations as well. But the benefits of this particular standard, much larger distances, you can link hotspots, etc. The throughput is not great, 54 meg per second, but if you consider the cost and what you're gaining from that, it's pretty cool. We have 802.11ad. This is an extremely high frequency. So if you look at that, that's way up there, 57 to 64 gigahertz. But the range is very, very short, only about 10 meters, but 7 gigabits of throughput. Now, there's actually a couple of applications for this, and this is the one that really will, I think, change home automation, change home connectivity, and quite a few other things. Because of the distance limitation, I'm not sure what the licensing requirements are. The downside to WiGig, which is what this is called, is that when you get to those higher frequencies, you can't transmit through walls and so on. You can do things like beamforming and whatnot, but with such a high frequency, you can't transmit through walls or people or whatever. The goal of this particular, and this is the thing that I find the coolest, is the goal of this standard, the AD standard, is that at least one of the applications is in your Wi-Fi system. I mean your hi-fi system. your media center, right? You have your stereo receiver, you've got your TV, you've got your DVD player, etc. Well, guess what's connecting all those components? Cables. And so with this standard, the idea is that everything will be wireless. You basically just plug things in, no more cables, and you can transmit everything over this spectrum. High throughput, 7 gigs of throughput, 5 gigs of throughput is going to be enough to support those applications. Kind of cool. Okay. All right. Let's go ahead and take a break. I'm going to pause the recording here. So the next thing that we're going to take a look at is the 2.4 gigahertz spectrum. We kind of alluded to some of the concepts of this earlier. The ISM band, the 2.4 gigahertz component of the ISM band, was planned with channels that are 22 megahertz wide, which you can see here. The channels also require 5 megahertz of separation from each other, so we don't have any sideband interference for the shoulders of the channels. There are actually 11 channels available in the United States and 13 in Europe and 14 in Japan. But if a device uses a channel that's 22 megahertz wide, 11 megahertz on each side of the peak frequency, the channel will encroach on the neighboring channels because there's only a 5 megahertz wide gap between those channels. That means two devices that use two overlapping channels in the same area will interfere with each other. So as a result, there are 3 non-overlapping channels in the United States, channels 1, channel 6, and channel 11. Any attempt to use channels that are closer to each other is going to result in something called co-channel interference. Non-overlapping channels need to be separated by at least 25 megahertz at the center frequency or by 5 channel bands in order so we don't have that overlap. In Europe, as many as 4 channels, 1, 6, 11, 1, 5, 9, and 13 can be used as long as we're using OFDM. Remember, OFDM only makes use of 20 megahertz of that 22 megahertz wide channel. European channels are a little bit closer together. They overlap a little bit more. That creates kind of a slightly higher average noise level. In Japan, also 4 channels, 1, 6, 11, and channel 14, as you can see there, which is kind of an offset, right, from the original 13 channels, but that was actually added for that purpose. Channel 14 is kind of separate from the other channels. All right, now channel 14 can only be used in 802.11b networks. You're not going to see channel 14 in either 802.11g or n. When two access points use channels that are too close to each other, what do you think is going to happen? We're going to create these things called channel interference or overlapping channel interference or co-channel interference. When two APs are located in the same area, if you're using non-overlapping channels, you won't have a problem. But if non-overlapping channels are not available, it's better the APs on the same channel than to put them in channels that are apart from each other, believe it or not. APs on the same channel will hear each other, and each will be able to detect that the other is transmitting. So when a Wi-Fi device transmits, it actually informs the cell in its header about the duration of the message. So the neighboring AP, which is actually in the same frequency range, will hear that information, and it actually stays quiet while the signal gets sent. Obviously, if you're sharing a channel, that's going to slow down both cells, but at least you're not competing with each other and causing interference. There will be some interference, right? Some clients on the first AP might send a signal without the second AP or its clients hearing the message, which could create collisions in the environment, and that's where we see that co-channel interference. If the two APs are 2 or 3 channels apart, they can still be distributed by the other signals, but they'll be unable to hear the other messages that state that duration of the emission that's being transmitted. So the result would be, again, another collision. But ultimately, in a good Wi-Fi design, only non-overlapping channels would be placed next to each other. In 802.11n, we allow for 40 megahertz wide channels for 2.4 gigahertz, but the implementation is really only feasible in residential deployments. Using 40 megahertz wide channels in the 2.4 gigahertz band obviously is going to reduce further the number of non-overlapping channels that I would have potentially available to me. Let's take a look at the 802.11a spectrum, namely in the 5 gigahertz range. The 5 gigahertz band is divided up into several sections. We talked about that in one of the previous slides, right? UNII 1, UNII 2, UNII 3, and so on. These channels are spaced at 20 megahertz intervals and are considered to be all the way through non-interfering. They do have overlap within the frequency spectrum. Certainly you can see that in the diagram here. But you can have consecutive channels that can be used in neighboring cell coverage, but the neighboring cells need to be separated by at least one channel when possible. So you'll see here that this channel here and this channel here, only the sideband, which are basically the unused frequencies, overlap in that particular case, and the center frequencies and the main band frequencies don't overlap. So it's a general best practice to skip at least one channel when you're dealing with 802.11a. Now, all that being said, when you're dealing with radio resource management in a wireless controller environment, you don't really have to worry about this because the system, lost my train of thought there for a second, the system will actually manage that. It will detect what channels are being interfered with, what frequencies are interfered with, and it'll automatically adjust itself accordingly, change the transmit power and receive power, change the channel, and so on. We'll talk about that when we get into the specifics of controller management and controller configurations. So we see the different frequencies. Remember, this is the lower band that you're looking at here, which is 36 is the default channel. Then you get into the middle band and the H band, where we have these 52 and 56 and 60 and 64. You're seeing the center frequency for each of the channels, 5260 and 5280 and 5300, obviously separated by 1 or 20 megahertz each. And then there's another H band, and then we see the upper band, channel 149, 153, 157, 161, and then we see the ISM band at 165. None of which are available in the ETSI specification, but are all available in the FCC specification. This goes back to what we saw in one of the previous slides when we were looking at the configuration. Now in 802.11, we have the ability to use 20 megahertz channels, 20 megahertz wide channels, and 40 megahertz wide channels. The 40 megahertz channels in 802.11n are essentially two adjacent 20 megahertz wide channels that get bonded together. When we're using a 40 megahertz bonded channel, 802.11n can then take advantage of the fact that each 20 megahertz channel receives a small part at the top and the bottom to reduce interference in the adjacent channels. If you're using 40 megahertz wide channels, the top of the lower channel and the bottom of the upper channel do not need to be reserved to avoid interference. In other words, these gaps here, right? The top and the bottom. The top of the lower channel, which is kind of this line right here, and the bottom of the upper channel, which is this line right here. You might think, well, this is going to cause interference. Well, not when the channels are aggregated together. All right, so we can actually use these parts of the channel to also carry information. by using two 20 megahertz channels, an 802.11 specification gives you more than double the actual data rate when you move from 20 to 40 megahertz channels. Aggregating channels loses backwards compatibility with 802.11 GNA devices because we don't operate with 40 megahertz wide channels in those spectrums, only 22 and 20 megahertz wide channels. We still use OFDM, just like we saw with 802.11a and G, but 802.11n increases the speed from 54 megs per second to 65 megabits per second for a 20 megahertz wide channel. And in a 40 megahertz channel scenario, the speed actually goes even higher. It goes up to about 135 megabits per second because it allows more than one signal to be transmitted at a time. Actually, you can transmit up to 4 signals at a time. Now that will get you a speed of up to about 600 megabits per second. So there's some significant differences here when we're dealing with these different designs and allocations of channel spacing. All right. We can even do further aggregation when we go into the 802.11ac specification. That's going to allow channels to be 20 megahertz wide, 40 megahertz wide, 80 megahertz wide, or even 160 megahertz wide. Channel bonding increases the data rates in the network. There are a few things, though, that you have to consider when you're dealing with these different specifications. If I'm doing 20 megahertz wide channels, there are a couple of things to consider with AC. If I'm using voice only, or if we have a lot of radar activity forcing channel changes, that would be a consideration I'd have to take into account. There's no need to have wideband transmission like aggregated channels for voice because it's such a low bandwidth application. So 20 megahertz works just fine in that scenario. If we have a lot of non-802.11n or AC capable 5 gigahertz clients, we want to stick with the 20 megahertz wide channels so we have that backwards compatibility to those 11.a clients. Small data requirements, medium data requirements, no need to do channel aggregation. If you have a lot of 11AC APs at 20 megahertz and you don't really plan to upgrade them, then of course you would stay with that. What about 40 megahertz wide? Streaming video is where this would sit, right? That's a much more high bandwidth application, bursty application. Heavy data usage, moderate data usage. What about 80 megahertz wide channels? If we're using if we've primarily switched to 11 AC clients, .11 AC capable clients, we have smartphones that operate in the AC space. We need faster throughput. High definition video streaming would fall under this category. Multimedia rich content applications would fall under this category. Medical documents, anything that's going to require a great amount of bandwidth, you would go up to this level. In applications for our clients, we've only utilized up to 40 megahertz wide channels in most cases. That usually meets most of the requirements that we have. But you never know. I mean, data applications are becoming much more and more bandwidth intensive. So, all right. Now, if you do change, obviously, if you aggregate these channels together, the number of channels that are available to you changes as well. At 20 megahertz, which is kind of the standard definition, you have 25 channels available to you in the United States, and you have 19 channels available to you with ETSI, or European Union. At 40 megahertz, goes down to about 12 channels, about half, it makes sense, about 9 channels in Europe. 80 megahertz, that's going to go in half again, about 6 channels, or 2 in Europe. And 120 megahertz, you're going to go down to about 2 channels. So there is a trade-off, right? There is a trade-off between the faster throughput versus the number of available channels to transmit and receive data. Just something to consider when you're dealing with these standards. All right. There is another consideration to take into account when you're dealing in the 5 gigahertz spectrum. We see certain channels, specifically in the UNII-2 and UNII-2 extended range in North America for DFS and TPC. TPC is transmission power control. And then we also have DFS, which is a standard, an ITU standard, to enforce restrictions that on channels that might interfere with marine, weather, or military radar applications. Okay. DFS dynamically essentially instructs an access point to switch to another channel if a particular set of conditions occur, like the presence of a radar signals being received or sent. Before transmitting, the DFS mechanism of the access point actually monitors the available spectrum and listens for radar signals. If it detects a signal, the channel that's associated with that signal is then vacated or flagged as unavailable for use by the transmitter in this particular case. This is a requirement. You have to have this capability built in because radar and marine radio and weather radio transmissions fall within the spectrum. TPC, another component, transmission power control, allows the AEP to negotiate power levels during the association process for the client that's connecting to the AEP and so on. So the AEP can actually inform the client of the range of allowable transmission power that can be used with that AEP, and it can actually reject clients that might not meet those particular levels. The client will then adjust its transmission power level within that range that was specified during that TCP negotiation to ensure that interference from the wireless LAN is minimized. It allows the wireless LAN client to optimize its battery life as well. If I can transmit at a lower power, then I might as well do that. All right. How is channel bonding affected by this, right? Adjacent channels get bonded to form, say, 40 megahertz wide channels or 80 megahertz wide channels. So we're bonding 2 channels together or 4 channels together. The AP is still going to monitor all those channels, and using the monitoring techniques, it will leave the channel if a DFS event occurs in the bonded area of that spectrum. So keep in mind, we're still going to affect those channels even though they're bonded together. And then we'll look for another part of the spectrum to set up a similar bonding scenario. If I can't find any clear spectrum space, I'll drop that whole segment of the spectrum and just won't use it. I might even go, say, from a 40 megahertz bond down to a 20 megahertz signal, or I would go from an 80 megahertz bond down to a 40 megahertz signal. All right. There are a couple of concepts within wireless controllers called DCA and RRM. I've already mentioned RRM, Radio Resource Management. DCA is Dynamic Channel Assignment. These are components that you can configure within a wireless controller to control the aspects of the spectrum. All right. All righty. So that concludes this particular lesson. I know it was a long one, right? A lot of information, a couple of hours that we talked about. But I think it's a lot of good information. We talked about spread spectrum technologies and FHSS and DSSS and the different spread spectrum components that we had. 1 megabit per second with dBPSK and 2 megabits per second with Quadrature PSK. And then we looked at CCK, OFDM, QAM, and 16 QAM, and 64 QAM, and 256 QAM. We talked about larger channels and how you have to manage that aspect, why it's very important to be able to manage that aspect. Talked about some of the emerging technologies as well, some of the sub-gigahertz wireless spectrums, and then we finally wrapped up with the 5 gigahertz channels and talked about DFS and so on. We'll get into some of that stuff in more detail later on as well. Well, this is not the only time we're going to talk about these concepts, so we will get into that stuff a little bit later on. But let's wrap up this lesson, and we're going to go ahead and move into our next lesson, which is media access. Looking at the wired side, talking about how frames are sent in the wireless network and then how those frames get bridged over to the wired side of the network. All right.